Right now, you're breathing. Your lungs expand and air fills the space inside you. But here's the strange part. You have no idea what you're actually breathing. You can't see it. Nobody can. But what if you could? What if tomorrow morning you woke up and suddenly the invisible became visible? The question sounds simple until you start thinking about what would actually happen to your world. The truth is, air is everywhere. It surrounds you constantly. It presses against your skin with a force of about 14.7 pounds per square inch right this very moment, and you don't feel it because you've never known anything different. But if you could see air the way you see water or soil or skin, your entire perception of reality would shatter in an instant. And the thing is, scientists have already figured out how to see it. They're just not using your eyes. In 1864, a German physicist named August Toepler invented something revolutionary called schlieren photography. The name comes from the German word for streaks. What Toepler discovered was that light doesn't travel in a perfectly straight line when it passes through air of different temperatures or densities. Instead, it bends, it refracts. And if you position a camera just right with mirrors and a knife edge, you can photograph that bending. You can see the invisible made visible. That first glimpse changed everything about how we understand aerodynamics, heat, and flow. But here's what Toepler's images showed that most people don't realize. If you could actually see air the way his camera could, you'd be looking at something unimaginably complex. Start with the molecules. In one single breath you take right now, you're inhaling approximately 1.3 times 10 to the 22nd molecules. That's 13 followed by 21 zeros. To put that in perspective, that's about the same as the number of stars in the entire observable universe. And you inhale that many molecules without thinking about it. The molecules themselves are so small that roughly 2.69 times 10 to the 22nd of them can fit inside a single liter of air. Imagine trying to see something that small. Imagine trying to watch 13 septillion individual particles all moving at different speeds in different directions, constantly colliding with each other 10 billion times per second per molecule. That collision rate is why air exists. Without it, there would be no such thing as air at all. There would just be individual molecules floating randomly through space. But because they collide so often, so densely, they create something that behaves like a fluid. They create what you breathe. Now here's where your eye evolved into the ultimate trap. Your eye is sensitive to visible light, which travels in wavelengths between about 380 and 700 nanometers. Those wavelengths are special because the nitrogen and oxygen molecules that make up 99% of your air don't absorb them. They let them pass straight through. Your eye evolved to be sensitive to light that passes through air unobstructed because that's what allowed you to see things at distance. The things that matter to survival: prey, predators, landmarks, danger. But the cost of that evolutionary advantage is that you became blind to the medium you move through every second of your life. Think about what water looks like. You can see it clearly in a glass or a lake or the ocean. But water is mostly transparent too. The difference is that water absorbs certain wavelengths of light much more strongly than air does, and it scatters light as the molecules are packed more densely. If water were as clear as air, you'd see nothing when you jumped in the ocean. You'd be suspended in an invisible void. Air is like that ocean, except you're inside it instead of outside it. And you've never questioned it because there's nothing to compare it to. You've never experienced the alternative. But let's imagine you could suddenly see air. What would appear in front of your face? First, you'd see movement everywhere. Not wind, necessarily, but the thermal currents rising from your skin. In your home, you'd see columns of hot air rising from light bulbs and radiators. You'd see cold air sinking from windows and air conditioning vents. The air would look almost like water, with visible streams and eddies and currents flowing in complex patterns. The German physicist Ernst Mach and his son Ludwig Mach discovered this in the 1880s when they started using Toepler's technique to photograph high-speed projectiles moving through air. What they saw was a revelation. Around the projectile, the air didn't move smoothly out of the way. Instead, it compressed, formed shock waves, created zones of wildly different density. The air was not a continuous medium. It was a turbulent ocean of constantly shifting pressure gradients and density variations. If you could see the air outside your window on a windy day, you wouldn't see a smooth flow. You'd see something chaotic. You'd see eddies and vortices forming and collapsing. Researchers have discovered through wind tunnel visualization that even relatively calm wind is full of turbulent structures at multiple scales. Bartosz Czekanowski, who creates interactive physics demonstrations, showed that even at hurricane-level wind speeds, individual air molecules barely appear to move relative to each other. That's the paradox of air. Vast macroscopic flows that look smooth and organized, but they're composed of individual molecules moving randomly in every direction. The bulk motion you can see with Schlieren photography is like watching the statistical average of chaos. The overall vector is one way, but almost half the molecules are moving the opposite direction. Now imagine you could see air even more clearly. Imagine you could see the individual molecules themselves. You'd be standing in what amounts to a fog of impossible density. At sea level, there are about 2.7 times 10 to the 19th molecules in every single cubic centimeter of air around you. If each molecule were the size of a grain of sand, and you tried to pack them into a cubic foot of space, you'd be crushed instantly. The reason you're not crushed is that those molecules are almost infinitely far apart relative to their size. The average spacing between molecules at sea level is roughly 10 times their diameter. That doesn't sound like much until you realize that means the air is 99.99% empty space. You are 99.99% empty space. Every breath you take is mostly nothingness. The molecules are just spread out enough to create the pressure and the substance of air. But here's what would actually be visible if you could see the molecular arrangement. You'd see a random structure, constantly shifting and reforming. You'd see hot air pockets where molecules are moving faster, spread further apart. You'd see cold pockets where molecules are moving slower, packed closer together. You'd see violent collisions occurring at a scale your brain couldn't even process. Billions of particles per second. And the stranger thing, that randomness is exactly what keeps you alive. If the molecules arranged themselves into an ordered pattern, or if they stopped moving, the air would become a solid. It would become ice, and you couldn't breathe. The chaos is the property that makes air possible. When you look at a dust mote floating through a sunbeam, you're actually seeing one of the few times air becomes partially visible. That dust mote is small, but not molecule small. It's large enough to be struck billions of times per second by air molecules, and each of those collisions pushes it in a random direction. The result is a jittering, random walk that's called Brownian motion. If you could see all the air molecules surrounding that dust mote, you'd see an ocean of impact, a constant bombardment of invisible strikes pushing it chaotically through space. For hundreds of years, scientists didn't even believe Brownian motion was real. They thought dust motes just moved randomly by accident. It wasn't until Albert Einstein wrote equations explaining the mathematics of molecular collisions in 1905 that scientists realized the dust wasn't moving randomly at all. It was moving because it was being hit by particles so small they were invisible. The universe was showing you the proof of atoms all along, and you just couldn't see it. If you could actually see air in fine detail, you'd also see something else: color. Pure air is colorless, but the way air bends light creates a subtle color gradient in the atmosphere. On a clear day, the sky is blue because of Rayleigh scattering, which means shorter wavelengths of light, the blues and purples, scatter more readily in air than longer wavelengths. But if you could see the air itself, not just its effect on light, you wouldn't see blue. You'd see the density gradients themselves. You'd see variations in refractive index as a kind of shimmer or distortion. The same way heat distorts the air above hot pavement. That shimmer would be everywhere. It would be the primary feature of every scene you look at, more visible than the objects themselves in many cases. The mountains would vanish behind waves of heat shimmer. Your bedroom would ripple with rising warm air. Every thermal difference would appear as a visible distortion. And here's the part that would truly transform your experience. You'd finally see wind, real wind, not leaves being blown, not hair being pushed, but the actual invisible force itself. Wind is just air moving from high pressure to low pressure. It's invisible because you can only perceive moving air by its effect on other things. But with the ability to see air itself, you'd watch wind as a real, visible phenomenon. You'd see why hurricanes spiral the way they do. You'd see the Coriolis effect not as an abstract concept, but as an actual visible pattern in the air itself. You'd watch cold fronts collide with warm air and see the boundary layer between them form and shift. You'd see dust devils not as small tornadoes but as visible columns of air rotation. The invisible would suddenly have shape and form and motion you could track with your eyes. Scientists who work with schlieren systems and computational fluid dynamics have discovered that airflow is infinitely more complex than our intuition suggests. A simple object like a cylinder has turbulent eddies forming downstream in patterns that take supercomputer models to fully predict. If you could see air, you'd watch those eddies form, collapse, and reform. You'd see vortices spiraling off in patterns that look almost alive. You'd see air seemingly taking on a mind of its own around your body, around buildings, around anything that moves. There's a reason it took centuries of scientific study to understand aerodynamics. The complexity of airflow is genuinely difficult to comprehend even when you can see it through instruments. But perhaps the strangest part of seeing air would be understanding what you've been missing your whole life. You've walked through storms without seeing what's actually happening. You've stood at the top of mountains and watched wind blow without watching what the wind actually is. You've felt temperature changes as abstract sensations instead of as visible gradients of molecular motion. You've breathed air without knowing what you're pulling into your lungs. Billions of molecules that have circulated through every lungs that's ever existed. Every dinosaur, every human being who ever lived. Every breath you take connects you to breath taken by people and creatures millions of years dead. But you can't see that connection. You can't see the medium of life itself. The question of whether you could see air is not really about whether your eyes could physically perceive those molecules. It's about whether you could process what you were seeing. The human brain can only hold so much visual information. Your attention is precious. If you could see air in full detail, you might go mad from the sheer complexity of it. The constant motion, the billions of collisions per second, the turbulent chaos underlying every apparently smooth motion. You'd see that the world you think is stable is actually in constant flux at every scale. You'd see that the invisible is infinitely more complex than the visible. You'd see that the medium you've ignored your whole life is the most important thing that's ever happened to you. And that's the point where you step back and look at the room around you. You look at the air filling the space between you and this screen. You remember what you can't see. You remember what August Toepler saw in his first schlieren photographs, what Ernst Mach's son discovered with high-speed imaging, what every visualization technique has revealed since then, that air is not empty, air is not simple, air is not invisible. It's only invisible to you. And maybe that's not a limitation of your biology at all. Maybe that's a gift. Maybe you can breathe without seeing it the same way you can live without understanding quantum mechanics. Maybe there's wisdom in not being able to see the infinite complexity of air surrounding you every moment. Because if you could see it, really see it, you might never take another breath without feeling the terrible weight of 10 quintillion molecules pressing against your skin, holding you to the earth, filling your lungs, connecting you to everyone who ever lived. Tonight, when the sun goes down and you turn off the lights, you'll be breathing air you can't see. And somewhere in the darkness, invisible to your eyes but visible to every instrument we've invented to measure it, the wind will blow and the molecules will collide and the chaos will continue. You'll be suspended in a medium so invisible that you've forgotten it exists. But it exists. It's always been there. And now you know what you're missing.